This is page 5 of the synchronization notes. And this is sort of another use case, but it's kind of big and weighty, so I'm going to give it its own section number. And it's called barrier synchronization. And barrier synchronization is really a generalization of a task rendezvous from two tasks to any number of tasks. So generalizes the rendezvous from two tasks to n tasks. So they all have to arrive at the barrier before any of them can proceed past it. So this is an illustration of that with 3 tasks. So we've got task 1, task 2, and task 3. And their initial state is all ready. So let's just say that we created these 3 threads in RTOS2, and then we start the scheduler. And they're going to execute in some kind of arbitrary order. It's concurrent execution, assuming they all have the same priority. So let's just say that task 1 proceeds first. So they're sharing a processor. It hits the barrier. So it gets to a place in the code where it performs the synchronization on the barrier. And at that point, it's the first one to arrive, so its state is going to change to blocked. And then let's say that task 2 executes and it gets as far as its barrier synchronization call. And it's the second one to arrive, so its state changes to blocked. And then task 3 runs last, and it arrives at the barrier at the point in the code where it's synchronizing with the barrier. And it's the nth task, or the last task to arrive. And so its state will remain at ready. So note that I'm not changing the state there. And at this point, then task 2 and task 1 also become ready. So let's just do a dashed line here. So at this point, any of them can proceed because they're all ready to run, and it's at the discretion of the scheduler, which will go next. So for argument's sake, let's just say that, let's say task 2 continues executing, and then when it's had its turn, task 3 will run, and then task 1 will run. And so that is an example of a barrier synchronization. And I guess I should label, this is time going down this way. So now we have to figure out how do we get from a 2-task rendezvous to n tasks. And I think I've got room to squeeze this on this page. So let's move up a little bit. So this is going to be a solution with 3 semaphores, and this is for 3 tasks. And so we are going to have semaphore S1 equal to 0, S2 equal to 0, and S3 equal to 0. So that's our starting condition. So now you should try to envisage how the 3 tasks will interact with those semaphores to implement a barrier. So they each, execute a bit, and then they want to synchronize. So task 1 will signal its semaphore, so signal S1. Task 2 will signal S2, and task 3 will signal S3. And then they want to wait. Just leave a blank line here. So say that task 1, it wants to wait for task 2 and task 3 to arrive. So it will do await S2 and await S3. Now at this point we can do a little arithmetic. So S1 has been changed to 1, S2 has been changed to 1, and S3 has been changed to 1 by those signals. Now task 1 comes along and it waits on S2, which takes it down to 0. It waits on S3, which brings it down to 0. But task 1 is not the only one that's going to wait on task 2. Task 3, or on S2. Task 3 is as well. So let's just keep going here. So task 2 wants to know that S1 has arrived and that task 3 has arrived. And task 3 wants to know that S1 has arrived and task 2 has arrived, so it waits S2. So the problem here is we're only incrementing the signal once, up to 1, but then if you just count across, S1 gets decremented twice here by 2 waits, and the same goes for S2 and S3. So the solution is to signal each one a second time. So signal S1 twice, task 2 will signal S2 twice, and task 3 will signal S3 twice. And this will guarantee that they will all wait until the last task arrives, and then they will all be able to proceed. And the problem with this solution is that the code grows as you add number of tasks, and also the number of semaphores that's required grows as well. It's not a good general solution, so not a good general solution. You can imagine if you had 20 tasks, this would get kind of unwieldy. So we're going to look at a solution that's a better general solution next.